Okay, so usually, by the way, I hear, let's say, more people say wa alaikum salam or so. It looks like you were angry of yesterday's quiz or so. I don't know. I hope, you know, I'm sure that the quiz was not trivial, but I hope that it was also not very difficult. Let's say probably there are some parts of it that are okay, and some parts may require us a bit of thinking or so. But anyway, let's leave the quiz for the time being. Inshallah, once I grade it, you can discuss it with me if you want. Right, let's do what we were talking about, or let's continue what we were talking about last class. I'll just remind you of the highlights of the main points. We said that systems have specific features, let's say. A system may be linear, it may not be linear. It may be causal, or it may not be causal. It may be stable, or it may not be stable, and so on. There were 6 or 7 different features. May be invertible, or it may not be invertible, and so on. Okay, so we've talked about 6 or 7 features, let's say, or properties of systems. And then we said, let's focus on a type of system which is called linear time invariant systems. Linear time invariant systems. Linear time invariant systems have 2 features that are of importance to us that we will focus on from now until most of the course, if not until the end of the course. Okay? So a system that is both linear and it's also time invariant is, let's say, those 2 features are of importance to us until the end of the semester, and we'll focus on systems that satisfy both of those 2 properties. I mentioned last class, or the previous 2 classes, that systems that are linear time invariant, I can either describe them by a relationship that tells me what is the input or how is the output related to the input. Like, for example, y of t is equal to 3x of t. This is an input-output relation. And I said that you can also describe linear time invariant systems using something which is called the impulse response. And I talked last class about the impulse response. What does it mean? Yeah, we said that the impulse response is nothing but the output of the system when its input is an impulse. And I explained to you, for example, that, and I was planning, last night I added maybe about 8, 9, 10 pages into the lecture note. I think it reached 40, 41, 42 pages now. So one of the things that I was talking about or one of the things that I just started talking about, but I haven't finished it, is examples of how do you find the impulse response. And I mentioned last class, I think, that you can find, for example, the impulse response in a sound system by clapping, by doing something like this. Okay, if you do something like this, the clap, okay, clapping produces a signal that looks like an impulse. And this impulse, when it goes into the system, it will appear at the other end, at the output, in a specific shape. The shape that appears at the output due to this input is nothing but the impulse response of that system. Okay? And there is a reason why we are talking about the impulse response, because starting from this point, we will discuss the systems by talking about their impulse responses. Meaning, instead of telling you, I have a system, a box, where this input is x and y is equal to 3x minus 2, for example, I'll tell you that I have a system, and that system has an impulse response, which is h of t equal to this much. I have, by telling you the impulse response, it's like exactly the same as if I have given you the input-output relationship. The point is that the impulse response is not defined for all types of systems. It's only defined, at least for the time being, think of it this way, it's only defined for linear and time invariant systems. Systems that are not linear or not time invariant, they do not have an impulse response. They have, but not in your course. Okay? So forget about systems that are not that are either not linear or not time invariant. And last class, I wanted to show you, okay, now we know the impulse response of the system. We put an impulse and we observe the output. And I'll show you some figures. I added a lot of figures there that hopefully will take you now to the process, in a nice way, hopefully. Okay? So we have determined the impulse response of a system. Now we have an input which is not an impulse. We have any general input which is x of t. Can you tell me what is the output y of t in terms of both the input x of t and the impulse response of the system? This is basically what we're trying to do now. Last class, I showed you those 3 properties and showed you basically that we did some substitution of variables in those 3 properties of the impulse function. and we came up with exactly the same properties, but they're just written in a different way. And instead of using t and t0, I'm using tau to replace t, and I'm using t to replace tz. And then we said that those three allow us to write any function x of t in this form as the integration from minus infinity to infinity of x, not of t, but x of tau, delta, or the impulse, evaluated at t minus tau. And the integration is with respect to tau. And the reason why I'm writing x of t this way is that I want to approximate x of t by, if you remember, I talked about this device last class. Yeah? I want to approximate it by an infinite number of impulses. Not only one impulse, but I want to define the function by an infinite number of impulses. And how what am I basically, what do I want to do? I said that assume that this is a function that, just change it to green. Assume that this is a function that I have. Let's say this is x of t. Okay. Now you can always represent x of t as x of t. Or you can always say that this x of t is equal to the value of x evaluated at this point, at the first point in here, multiplied by a rectangle. Think of each one of those pieces there as an impulse. But I'll approximate the impulse by small rectangle, a thin rectangle. So each one of those, you can think of it as a rectangle. And if you zoom in, I don't know if you can see it or not, but if you zoom in, this is nothing but, it looks like a small rectangle like that. Right? So I will say that this x of t is basically equal to x at minus 3 multiplied by a rectangle. Let me just do it like this. Multiplied by a rectangle that happens at minus 3. But it's not only this. This now, what I have done in here, it only produced to me the value of that function x of t at only one point, which is x of minus 3. I need to add to it also x of minus 2.9, for example, multiplied by an impulse, or what looks like an impulse, an approximation of an impulse, which is a rectangle that happens at minus 2.9. Sorry, this is minus 2.9. Okay, and so on. If I keep doing this plus infinite of those, and not only, I'm using rectangles here. In the limit, if the rectangle width becomes equal to 0, I will see that all of this basically becomes equal to that. This is basically what I'm trying to say. Okay? So this formula that I have just written a minute ago, this formula in here, okay, this formula, I can write it in a way that looks like this. Okay? This is exactly the formula that I have on top. I'll just replace the integration with summation. Sum of infinite number of impulses or infinite number of rectangles, let's say. Okay? Where in the limit, as the width of the rectangle approaches 0, I'll go from here to here. Now, what do I have in there? I have the value of the function x, but not evaluated at tau or at, okay? Evaluated at k multiplied by epsilon. Okay? Multiplied by a rectangle. This basically simulates the impulse, and this simulates the value of the function at different values. As epsilon approaches 0, trust me on this, this becomes equal to this thing. Okay? Fine. Now, why am I doing all of this? I want you also to notice this, that this thing, the rectangle function, rect function, okay, with a small width epsilon, okay, approaches delta of t when epsilon approaches 0. And a shifted version of it will approach the shifted version of delta again when epsilon approaches 0. Okay? So those are things that, okay? Now, we know that if you put an impulse into a system with an impulse response, which is h of t, what is the output? By definition, I put an impulse into a system with an impulse response that is equal to h. Then the output I expect it to be equal to, basically the impulse response will appear at the output. Because this is how we define the impulse response. We said the impulse response of a system, put an impulse, observe the output. Now we define that system to have this impulse response, h of t. So clearly, if I put an impulse, all I have to do is just see what is the shape of this h of t, and this is what I'll get at the output. Okay, so this is, I haven't said much beyond what I said last class. Now, instead of putting this impulse, let me put something that approximates the impulse, which is this rectangle function. And let's make sure that the rectangle function there is narrow, meaning it's not 3 seconds wide, it's 0.001, for example, of a second wide. And this is the impulse. Okay, it has 0 width. I'll put something, and I don't know why I'm insisting on using this thick line. This is the impulse. I'll put something that is not really an impulse, but it's like a rectangle, but thin rectangle that approximates the impulse. And again, if I take the limit, I make the width here approach 0, the height will become equal to infinity. The area, I have made sure that it is equal to 1, so that this basically becomes equal to this. Now, clearly, if I put something that approximates the impulse, I'm not going to get the impulse response at the output. I'll get something that approximates the impulse response. This is why I put in here that this is an approximation. It's not really equal to the impulse response, but it's something that appears to be equal to the impulse response. Yeah, maybe a little bit distorted. Yeah, think of it this way. Slightly distorted from the version of the impulse response because of the fact that this is not exactly equal to the impulse. The closer this thing is to the impulse, the closer this becomes equal to the impulse response. Okay. Now, because we are limiting our discussion to time invariant systems, if we have a time invariant system, you see, if the system that we're working on is not time invariant, I wouldn't be able to do the step that I'm doing right now. But because we are saying that we are limiting our discussion to time invariant systems, because we are limiting our discussion to time invariant systems, I'll be able to do the next step that I'm going to show you. What am I doing in the next step? I'm saying, okay, and instead of putting this thing that approximates an impulse, let's put the same thing, but shift it by a specific amount. Yeah, put a delayed version of this, or put a shifted version of this. So basically, this becomes, let me show you both on top of each other. Okay, look, this is the input about in here. And the input that I'm putting there is exactly the same, but I'm removing every t and replacing it with t minus k epsilon. So it's kind of a shifted version of what I have above. Yeah, this here, if you shift in time, you end up with this. Because the system is time invariant, if I shift by a specific amount, which is equal to k epsilon, the system will respond by shifting its output by the same amount. And this is why at the output there, I'll end up with exactly the same thing that I got above, but shifted by the same amount. Okay? So the fact that it is time invariant allowed me to know this. This is what will happen. Okay. Now, because we are talking about a linear system, we said that the system is also linear. And what's the feature of linear systems? If you put two inputs, the outputs, let's say put an input, get an output. Put another input, get another output. If you put the addition of the two inputs, you get the addition of the two outputs. In fact, and this applies even if you put 3 inputs or 5 inputs or 10 inputs, just get the individual outputs and add them, you get the overall output. So in here, what I'm doing now is I'm putting a sum, an infinite sum of infinite number of those inputs. And each one of those inputs is just a shifted version of the other inputs. Okay, and if you notice in here, I'm summing, not summing with a variable here that is equal to r or if or something. Okay, I'm summing with a variable, the variable of the summation there is k, and each one of those, what looks like an impulse, is shifted by a different amount that depends on k, which means that the sum that I have there is an infinite number of delayed versions of those impulses or those rectangles. One that appears at this place, one appears a little bit later, one appears a little bit later, one appears a little bit later, and so on. Okay? So if I put a sum of inputs like that, I expect the output to be the sum of all previous outputs. Yani, this is the output due to one of the inputs. Okay? The upper one is the output due to only one input. Get the output due to the second input, get the output due to the third input, fourth input, and so on. If you add all of those, you get the overall output. And I was able to do this because of linearity. Okay? If the system was not linear, I wouldn't be able to do this. So we saw that because it was time invariant, I was able to do something. Because it is linear, I was able to do something else. Towards getting the answer that I want. Okay? Now, the last thing that I'll do is also because of linearity. This also has to do with linearity. What if I scale? You see in here, all of those impulses in this formula in here, all of those impulses, or what look like impulses, have the same height. Think of it this way. All of them are rectangles with the same height. Right? The height is 1 over epsilon. What if I scale those heights based on x of t itself? And each one of them will have a different height now. Not all equal height. Like, what's the difference between this device in here? In here, all of the impulses or so have the same height. All of them are flat. Basically, I'm producing something that looks like a constant function. While in here, different impulses there have different height that depends on the function x of t. I'm multiplying the value of x of t by each one of those impulses or rectangles to scale it up or down. And this is basically what I'm saying in here. I'm scaling each one of those impulses by the value of the function at that location. Trust me on this. If you scale the inputs, you'll scale the outputs because, again, the system is linear. So I have added this in here. I would have to add the same thing in the output. Okay? Now we're almost done. Now, all you have to know is that k epsilon in the limit, when epsilon approaches 0, this basically can be replaced by a continuous variable that is called tau. So wherever you see k epsilon in the limit as the limit of epsilon approach 0, wherever you see k epsilon, remove it and replace it with tau. So in here, k epsilon will become equal to tau. And the summation, by the way, will change to integration from minus infinity to infinity. Okay? So in here, I'll get x of tau. And in here, I'll get... okay. Well, this becomes equal to tau, but the whole thing here becomes nothing but the impulse function. I'll come to your question, Jihad. Just give me a minute, okay? So basically, in the limit as epsilon approaches 0, this becomes x of tau, and this becomes equal to delta of t minus tau. Without going into the math, how this happens, you need to trust me on this, okay? And if you notice that what happened on top is we said that this thing is nothing but x of t. So by doing this, in here, I could have removed all of this and said that in the limit, this becomes equal to x of t. The whole thing there becomes equal to x of t if I set epsilon to be equal to 0. Now let's look at the output. What will the output be in the limit as epsilon approaches 0? The output in here, if you notice, this is the output, which is exactly equal to this. In the limit as epsilon approaches 0, this becomes equal to x of tau, and this becomes equal to h of t minus tau. And this is basically the result that I'm interested in, which is equal to y of t. Which means that this is basically the conclusion. This is the final conclusion. If I have a system with an impulse response that is equal to h of t, if I feed in here delta of t, I expect the output y of t to be equal to h of t. This is what we call the impulse response. Now, if I remove this impulse and put x of t in general, any function now, put any function in the world as an input to that linear time invariant system, the output y of t will be equal to the integration from minus infinity to infinity of x of tau, where tau is a dummy variable. Tau, I could have called it alpha or zeta or whatever, any value, or a or b, or okay. Tau is nothing but a dummy variable. Okay? So this will be, y of t will be equal to the integration of x of tau multiplied by h of t minus tau, d tau. You're integrating with respect to tau. And we know that whenever you integrate any function with respect to a variable, let's say the integration of x of t dt the integration of x of t dt, or let's say for example of t squared, a function of t. The integration of t squared dt will be equal to t cubed divided by 3 plus constant. This is if we integrate. This is what we call indefinite integration, where you don't have limits. But once you put limits in here, for example, from -3 to 2, or -5 to 5, or -infinity to infinity, any limits, any numbers there, whether they're infinity or not, then the answer clearly you have to substitute for t equal to, for example, -infinity to infinity, for example, or whatever limits you have. The output will no longer have t. Whenever you integrate, whenever you have definite integration, meaning the limits, there are limits for the integration. Whenever you integrate with respect to any variable, the output does not have that variable. Which means that if you look at this integration, this is very important, because as you'll see, inshallah, in a few minutes, we will try to evaluate this for several examples. If you notice, gentlemen, here, I have the integration there from -infinity to infinity with respect to tau. And I have inside the integration two functions. One of them has tau in it. It's a function of tau. And the other one is a function of both t and tau. When I do this integration with respect to tau, okay, I expect the answer not to be, if someone tells you that the answer of this, for example, is equal to t minus tau squared, for example, you can immediately say that this is wrong. It cannot be. Why? I'm integrating with respect to tau, and the integration has definite limits. It's not integration, it's not the integration of t. It's the integration from -infinity to infinity of t, something like this. So the output should not, I'm integrating here with respect to tau. So the output should not have tau. But can the output have t in it? And the answer is yes. H is a function of both two variables, t and tau. So when you do the integration, tau will disappear, but t will remain. Now there are special cases in which the output may not depend on t. But those are special cases. But in general, the output will depend on t, but it will never, and I stress this, it will never depend on tau. If I give you, let's say, it's multiple choice question, and I tell you that I have done this integration, and the answer y of t was equal to, as I mentioned, t minus 3 tau, for example. Is this possible? Wrong. It cannot be. It's equal to 7 constant. Could it be? Yes, it's possible. It's equal to t cubed. Is it possible? Yes. But it cannot be t, it cannot have tau in the output. Because again, I'm integrating with respect to tau, and I have limits. So the limits there will be substituted for tau after I do the integration. So tau will disappear. Okay? Now there is a famous name for this integration. And I mentioned it, I think, in the second class of the course. Okay? This is called the convolution integral. Or you'll hear me say convolution, okay? So whenever I say convolution, I'm talking about this. And you need to memorize it. This is something like memorizing your name, let's say, okay? As an electrical engineer, you need to understand convolution. Not only know the formula. Anyone can memorize it in 2 minutes or so. You probably can write it 5 times and you'll be able to memorize it. But you need to know how to evaluate it. And here's the problem. Sometimes I need to maybe just shut up and not say things like what I'm going to say right now, okay? Or what I've said even in the past. The integration, this convolution integral, is not easy to evaluate. But once you understand the process, it will become easier to evaluate. Okay? Saying something like this will just let some of you shut their brains. Basically, you think that I'm one of those who always struggle with math. And what he is saying that it's difficult to evaluate, so forget it. I'm not even going to try. Please, I'm not saying this to kind of let you just stop thinking or think that you will never be able to. By the way, did I start recording or not? Yeah, okay. I'm not saying this just to shut you out, gentlemen, okay? I just want to let you know that there is a process for doing this convolution integral or for evaluating the convolution integral. And inshallah, in a few minutes, you see at least one example, and I'll also solve another example maybe. If I don't have time today, inshallah, we'll do it next class. Okay. But if you understand, trust me on this, once you understand the process for, let's say, very well for one example, you should be able to do it for any example. It's just that doing it the first time sometimes is a little bit tricky, let's say, okay? Or you might get stuck at a specific place here or there. But believe me, once you understand it, you should be able to solve for any problem, no matter how complicated it is. Because the process is, relatively speaking, complicated, if I give you a problem like this in a quiz or an exam, I'll make sure that the problem is, relatively speaking, simple. I'm not going to give you something that is too complicated that even I will struggle in solving. Okay? But anyway, this is called the convolution integral. The first thing I will do before we just continue further is, let's talk about some of the properties of the convolution integral. This is the convolution integral, okay? And as I mentioned, you need to memorize it. By the way, one of the things that I always like to think, I remember that I was discussing something with a colleague. I think he was a mechanical engineer or some other, I don't remember who it was, but I remember that this discussion was held between me and you, between me and someone else, okay, who was from not an electrical engineer. And we were discussing basically, I think, which field is better. If I recall correctly, I think this was the discussion. And I think, I don't know, was it me? It was a discussion among many people, from, I think, 2 departments or so. And someone basically said that we, as electrical engineers, we know how to do convolution integral. Do you know what convolution integral? And the gentleman said, what is convolution integral? And we just basically said, if you don't know what convolution integral, this means that electrical engineers are superior to your field. Something like that, okay? Knowing the convolution integral will appear not only in electrical engineering, it will appear in a lot of fields, system engineering, even the course that I'm teaching, the other course, which is probability. Believe me, in week number 5 or so, we will discuss the convolution integral. It will appear in the course. So it appears in different fields, not only electrical engineering. We as electrical engineers, we always like to pride ourselves that we are smart. And knowing how to do the convolution integral means that you can do any type of integration. Okay? There are some properties of the convolution integral, which is this thing. First of all, the convolution integral, each time I want to say convolution, I'm not going to write this formula. You see me sometimes do this. The convolution integral sometimes will be simplified, or there's another simplified form of it, or simplified version of it. I can say that this is the convolution of 2 signals, x of t convolved with, and this is the symbol that we will use, the star. It's not times. This is the, if you have a keyboard in front of you, it's above number 8. If you have number 8, shift number 8, it will give you that star. Well, some of the, I'm not sure, is it going to give you the 5? Let me just verify. Let me do something. Shift 8. Wallah. Okay, anyway, this is the star that usually is above number 8. Okay? This is the star of the, or let's say the symbol that is above number 8. Shift number 8, it will give you that symbol. Right? So the convolution integral is very often written this way. It's the convolution between 2 signals, x of t and h of t. Now, one of you may say, how come in here in the convolution we have tau, but in here we don't see tau? Yes, we don't see tau because tau is just a dummy variable of integration. When you want to convert this, when you want to evaluate it, the way you evaluate it is you'll have to convert it into that convolution integral. So you say that it's equal to minus infinity, the integration from minus infinity to infinity of x, and you replace the t with tau and multiply it by h, not of tau, but h of t minus tau. And the dummy variable of integration is tau. So this is how you convert from this to this and vice versa. Okay? One of the features or one of the properties of the convolution integral is that it is symmetric, or it's commutative. Okay? Meaning that if I find the convolution between x and h, it will be exactly as the convolution between h and x. Now this has some implication. The first formula here says the integration from minus infinity to infinity. Let me just reduce the font, so let's say the print size. So this is the integration from minus infinity to infinity. According to what I've just written, this is x of tau multiplied by h of t minus tau d tau. While the second one would look like this. It's the integration from minus infinity to infinity of, I'll start with the h in here. It will be h of tau times x of t minus tau d tau. So in fact, those are equal to each other. So it doesn't make any difference. If you put, this is basically what it says. If you have a system with an input x and an impulse response h, and another system with an impulse response not h but x, and you feed it with an input that is equal to h. This is basically what I'm saying. You have two systems, h of t, let's say this is the output y of t, and this is x of t. Assume that you have another system, completely different system, but you fed, or let's say that system has an impulse response, which I will call the impulse response of that system x of t. And I go and feed it with h of t, which is the impulse response of this. Both systems will have the same output. This is basically what they say. Okay? And basically this says that if you convolve x with h, it's exactly like convolving h with x. It doesn't make any difference. This is basically what we mean by commutative. And then the associative law also applies. If you have three systems, or let's say the convolution of three functions, x convolved with h convolved with q or whatever, you can always take the convolution of the first two and then convolve it with the third, or you can take the convolution of the last two and convolve the first with those two. And also you can distribute the convolution. If you have the addition of two h's and you convolve it with x, you can say that this is going to be equal to x convolved with h1 plus x convolved with h2. Or you can also do it this way. If you have two signals, x1 and x2, that are added, and then you feed them to a system with an impulse response h, you can find the output due to the first input only, which is h1 convolved with, x1 convolved with h, and find the output due to the second input alone, x2 convolved with h. Add them, you'll get exactly the same answer. Okay, so those are straightforward. I do not need to discuss them further. Okay, but let's now look at how you can convolve two signals. Right? I have done this. In fact, well, it took from me a lot of time yesterday. Right? To do this, I have listed steps. Okay, that you do not have to follow exactly, but those are good steps that probably will guide you on what you need to do to find the convolution. And then I had the time, honestly, to just do the convolution for one example, or solve one convolution example. Right? I wanted to solve at least one more example, but I didn't have time. And by the way, it's about 4 pages. The solution is about 4 pages, but it doesn't mean that any convolution will take you 4 pages or so. It's just that I was going step by step to illustrate for you how to do the convolution, and this is why it took a lot of pages. Okay, but trust me, I could have done it probably in 10 minutes or so. If I was doing it by hand, I would probably have been able to do this convolution maybe in 5 minutes, 10 minutes. So this is, really speaking, an easy example. It just took 4 pages, as I mentioned, because I was doing it step by step. Let me read for you the steps. Okay, and then I will explain the steps on the example. Right? And by the way, I'm not saying that those steps are Quran Munazzal. Those are just steps you can follow. If you understand them, you probably can skip some of them. It's just that I think, if at least at the beginning, try to follow those steps. Once you feel confident that you understand the convolution, you probably can skip some of those, or you can just bypass some of the steps there. Okay? Right. Okay, step number 1. Whenever I give you any example, let's say I'll give you some x of t, and I'll give you some h of t, and ask you find x of t convolved with h of t. typically this will be the problem that I'll give you. Okay, you need to do the following steps. I'm telling you at the beginning, determine how many pieces do each of those signals, and how many pieces are used to define each one of those signals. Let me explain it to you this way. Let me explain to you this step this way. Whenever you define signals, gentlemen, mathematically, you see generally, not always, but in most situations, signals will either be defined in this, where is it? Will either be defined like this, x of t is equal to sine 3t, for example. Now, if I ask you, what values of t can I plug into this sign, you're going to tell me any value. T equal to 1,000, minus 5, 10, 100, million, minus a million, any value of t that you're interested in, just plug it in place of t here, and you'll get the answer, the value of x of t at that point. Okay? We say that this is a function that is defined for all time, in one piece. Also, if I give you a function like this, e to the power of minus 5t, this is also a function that is defined for all time in one piece. I do not need to tell you here, t goes between minus infinity and infinity. It's by default. And for any value of t, you can just plug the value of t in here, and you'll be able to get the value of x of t. It could be large, it could be small. This is not the issue. I'll be able to get what x of t is. Now, there are some functions that are defined in what we call piecewise defined function that look like this, where for a specific range of t, I have a specific definition of the function. For another range of t, I have a second definition. For a third range of t, I have a third definition, and maybe more. Maybe I have 4 or 5 or 6 or 7 regions, or maybe only two regions. Those functions are defined in one piece, while this function, for example, the lower one, is defined in 3 pieces, 3 parts. Okay? What I'm talking about in step number 1 there is determine how many pieces, and I'm sorry, I'm not sure, is this the correct spelling for piece or not? I think, okay? Determine how many pieces is a function defined in. Like, for example, the first 2 examples that I gave you, those are single pieces. Each function has single piece. For the second one, I had 3 pieces. Let me just think of those as nx and nh. So, for example, let's say the signal x has 3 pieces, while the signal h has 5 pieces. For example, let's just for the sake of argument, let's say nx equal to 3 and nh equal to 7. Now, what's the implication of this? If you have a situation like this where one of the functions has more pieces or is defined over more pieces than the other, okay, there are generally the two forms of the convolution. Either the first form that I mentioned a few minutes ago, or the second form where you reverse the h and the x, the location of the x and h. Okay? If you have nx smaller than nh, if nx, or let me write it this way, if nh is smaller than nx, okay, use this form, and you'll understand why in a few minutes. Okay, if nh is greater than nx, use this form. It doesn't mean that if nh is greater than nx and you decided to use the first form, you'll get wrong. No, it's perfectly okay. It's just that it will become slightly more complicated to you. Okay, it will become slightly more complicated. If you understand the concept, you should be able to do it without any issue. It's just that it will become slightly more complicated to you. Okay, Akhwan? Do you have questions so far? Claude, Ahmed.
Yes, Doctor. What do you mean by NH and
okay. NX? Okay, sorry, I thought that maybe I explained them. Maybe I didn't explain them well. NH and NX, think of them as how many pieces is the function, how many pieces is the definition of the function occupying. For example, in the case in here, assume that this is x of t. All of those are x of t. I call them all x of t. Let me just erase, okay. In here, nx will be equal to 1. It's just one piece. Look, from minus infinity to infinity, I'm defining the function over a single definition. There's only a single definition that defines the function for all t, from minus infinity to infinity. صح? The same thing for this. nx is equal to 1. However, this function in here, I have nx equal to 3. Because for a specific range of x, specific range of t, this is the definition of, let me highlight it. This is the definition of the function for this range of t. And this is the definition of the function for this range of t. And this is the definition of the function for this range of t. So I have 3 regions in which the function changes depending on the value of t. So I'm thinking of nx in here to be equal to 3 regions. H of t could also be defined in the same way. And for example, h of t, maybe h of t will be equal to the following: 3t, 2t minus 5, t squared, 4 sine t, 5 cosine 3t, for example, okay? Where this thing is for t less than minus 5. This is t less than 3, less than minus 3, greater than minus 5. This is for t less than 1, greater than minus 3. This is for t less than 3, greater than 1. And this is for t greater than 1, okay? So in here, h itself, I'm defining it using 5 different regions. So in this situation, think of it in h, the number of pieces of h, to be equal to 5. Okay, Ahmed, did I answer the question?
Yes, but how can I distinguish the number of n from the graphs? Or we won't have to do that?
No, even if you had a graph, okay, let's say that you had a graph. Okay, thank you so much for pointing this out, because I was thinking of it mathematically. Let's say that you have a graph. I graphed for you the function. I gave you the functions in the form of a graph, and I told you, for example, that the function x looks like this, and then suddenly at a specific point in here, it does something like this, and then in here it becomes, for example, something like this. So you know that this is x of t. Let's say this is x of t. X of t has a definition here which looks like a cosine or sine. It has a constant in here, a definition which is like a constant in here, and it has something that looks like e to the power of minus x in here. So it is again 3 regions. Okay?
Okay, from the behavior of the function, right?
From the shape of the function, yes.
Okay.
Okay? Right. Okay. So what I'm saying here, gentlemen, in step number 1 is, depending on which is larger, it is recommended. It's not, if you just ignore this, nothing is going to happen. But trust me, sometimes it becomes slightly more complicated if you do this or do that. Okay? In many situations, you'll find that it doesn't make any difference, because this is defined in 2 pieces and this is defined in 2 pieces, for example. Okay? But in general, if this is true, if you have one of those 2 possibilities, okay, use this form or this form. Now, does it mean that you have to memorize this? No. You'll understand why this is when I go to the next few steps. Okay? But understand that this is what I will probably do. Right. And this basically the first 2 steps I'm saying here. It is preferred to use form 1. Okay? If nx, I hope that I didn't mess them up. If nx is greater than nh, yeah, nh, when nh is smaller than nx, use form 1. Maybe I wrote it kind of the opposite. Nx is greater than in here, while in there I said nh is smaller than. Okay? So this basically use form 1, and the opposite one use form 2. Okay, good. Any questions so far? Right. Now, what I'm going to ask you to do is, I want you to sketch, if you are using form 1, sketch x of t. If you are using if you are using form 2, and let me just remind you of form 1 and form 2. Let me just erase the mess that I have in there. Okay. If you are using form 1, this is form 1, I want you to sketch this function, x of t, but then I want you to go and remove every t and replace it with tau. Usually, if I give you a function, I'll tell you this is x of t. I'm not going to tell you that this is x of tau. So I want you to sketch it, but I want you to replace every t with tau. Every t has to be replaced with tau. So I'm saying x of t, if you are using form 1, or if you are using form 2, I want you to sketch h of t, not x of t, but h of t. Okay. However, when you sketch x of t, okay, and or h of t, depending on which form, I want you to make sure that you replace t wherever you see every t that appears in the function. I want you to replace it with tau. What do I mean by this? Assume that I gave you, for example, x of t to be equal to e to the power of minus 2t, for example, or minus t. Let me even make it simple. Okay, I told you that this is the function that you have. So I want you to sketch x of t. Okay, now if you sketch x of t, this is how it will look like. It's that dropping or decaying exponential, an exponential that becomes smaller. Now this thing is x of t, which is defined as e to the power of minus t. So this is x of t. What is the x-axis? It's t, right? So I have sketched x of t. I want you now to go and wherever you see t, replace it with tau. So clearly, in t in here, in the function itself, I'll have to write this as tau. And this is important, by the way. This is not something that you should take lightly. You have to understand. You have to do this. Not only there, the x-axis was called t. It's the t-axis. Now it will become the tau axis. Not only that, the function itself had e to the power of minus t. I'll have to write it as e to the power of minus tau. So I have replaced now every t with tau. So if this was h of t, I'll have to do the same process if I was using the other form. So I'll have to write h of tau, and wherever I see t, replace it with tau. Okay? So this is basically sketch. Okay, so this is point number 3. Now point number 4 is probably the most, not the most complicated, but it's one of the, let's say, most complicated steps of the process. Now we have sketched x of t because let's say we are using form 1, or we have sketched h of t because we are using form 2. So we have done already this or this, depending on which form we are doing. What remains, if we're using form 1, now we have to work with this. Or if we're using form 2, we have to work with this. So now comes the time for either plotting h, okay, or plotting x, depending on which form we have. I'm saying the following. I want you now to sketch under the first sketch, not to the side of it. Trust me. Don't, this is x of t. Don't do this. If you do this, you'll probably make a mistake. H of whatever, okay? Do not come in here and sketch H. Please do not do this. Do not sketch it to the side of it. You have to sketch it not here, but you have to sketch it here. Under it. Or above it, if you want to. Under it or above it. But not to its side. To its side, it's not going to help you. You have to do it under it. I don't know if I wrote the word under or not. I think I did. Anyway, I wrote it late at night, so maybe I didn't try this. But please, sketch it under it, okay? What am I asking you to do? I'm asking you to sketch h of t. So we have x of t, let's say above. Now I want you to sketch h of t. Let's say, for example, h of t looks like this. Let me even change it a little bit. Assume that this is h of t, or let me select maybe a different. Assume that this is h of t. Yeah, I just chose a random function. Let's say it's not for any specific reason. Okay, so I chose h of t there. I sketched h of t here. Right? I'm assuming that I'm using now form 1. If you're using form 2, you'll sketch x of t. Okay, which is the second thing in here. Okay, because I'm using form 1, I'll do it on this, and the other form is exactly the same, except that I'll be working with x. Now, what am I saying in here? Sketch the signal h of t if you're using form 1, or x of t if you're using form 2. Now, the sketch of h of t or x of t should be flipped first about the y-axis. This is something that you will also have to do. This is non-negotiable. I may allow you to do this point number 1 or point number 2, or may skip them. It's not going to make that much difference. But point number 3 and point number 4, you have to do them as they are. There is no, let's say, playing with those two steps. You have to do them as I'm saying. Okay? So first of all, you have to flip them around the y-axis. What do I mean by this? So now I have plotted h of t. I need to flip them around the y-axis. First of all, I think I don't remember. Hold on, let me see. Yeah, okay. Yeah, let me flip them around the y-axis. Flip only h of t around the y-axis. So how am I going to flip it around the y-axis? This is the y-axis. Put the mirror image of it. Exactly a mirror image of it. This function now, the way I have sketched it, is all to the right of the y-axis. So when you flip it, it will all appear. Sorry, the sketch is not perfect, but I am sure that you understand the concept, okay? So the whole figure will appear to the left of the y-axis. If the original function was doing something like this, then when you flip it, it will do something like this, okay? Yani depending on the shape of the function, maybe when you flip it around the y-axis, part of it will still be to the right and part of it will be to the left. The way I have, the way h of t was, all of it was to the right of the y-axis, so all of it now, when you flip it, it becomes to the left of the y-axis. Now, if this is h of t, clearly this thing is h of minus t. So I'll go and replace h of t here with h of minus t. I don't need h of t, by the way. So this is now h of minus t. This is minus t. Okay? Now, step number, let's say, still, we're in the same step. We're still in the same step, okay? So we have just flipped x or h, depending on which one we're sketching, around the y-axis. Now, I want you to go and replace every t with tau. Every t replaced with tau. So h, it becomes here h of minus tau. And this becomes h of minus tau. And if I had a function here, for example, assume that this was e to the power of minus t, I'll have to remove the t and there replace it with minus tau. Okay? So this is part B of step number 4. Part C of the same step, it says the following. Now I want you to take that thing, which is h, and shift it all the way to minus infinity. Tau equal to minus infinity. Yeah. Okay. I want you to shift it, okay, such that this point, and please pay attention to this here. You see this point? This point was tau equal to 0. صح? Remember that the x-axis now is tau. So this point in here is tau equal to 0. I want you to take this point and imagine in your head that you're shifting it all the way such that this comes, go to tau equal to minus infinity. Which means that this function now, I'll carry it and shift it all the way to the left. It will go all the way to minus infinity. I do not have a piece of paper that is wide enough to put minus infinity. But at least I will have to make sure that I think that this function in here has been shifted all the way, and I hope that I have sketched it properly, okay? That I put it at a location that is equal to minus infinity. Now the point in here, please pay attention to this. Tau equal to 0. If you notice, originally I had the function like that. Assume that this point was 1 or minus 1. If you shift this all the way to minus infinity, this point, think of it as minus infinity minus 1. 1 point to its left. Okay? Again, if I take this point in here and shift it all the way to minus infinity, this becomes equal to tau equal to minus infinity. So this point, think of it as tau equal to minus infinity minus 1. Okay? So I'm taking the function and shifting it all the way to minus infinity. Everything remains in this function, remains exactly in the same position of itself, except that everything has been shifted to minus infinity. Meaning this point will come here to minus infinity, and any point that is to the left of it or to the right of it will go to minus infinity plus 2 or minus infinity minus 1 and so on. Okay? In fact, think of the minus infinity there as an amount that is equal to t. Yani basically, I'm shifting that function by an amount that is equal to t, and I'm setting t to be equal to minus infinity. Okay? Again, let me say it. What I'm doing, gentlemen, and this is why I need to stress this point, because this is probably one of the most important points. This is what I'm doing. And maybe I'll repeat this point again so that I make sure that you understand it. And trust me, you're not going to understand the process perfectly until we solve at least 1 or 2 problems. So we had the function in here, something like that. We flipped it. So we got h of minus t. And then we removed the t and replaced it with tau. So we got h of minus tau, which looked like this. Now what I'm doing is I'm saying, let me remove every minus tau and replace it with t minus tau. Meaning I'm shifting by an amount that is equal to t. Remember that the x-axis is tau, it's not t. So t appears in this figure just like a constant. It's not variable, it's just like a constant. In this figure, t will appear like a constant, it's not the variable time. Just like a constant with a value that is equal to t. So I will shift this function, h of minus tau, by an amount that is equal to t and set t to be equal to minus infinity. Which means that the point which is at tau equal to 0 would become at tau equal to t. So this is the point tau equal to t, which is equal to, in this example, equal to minus infinity. And this point, which happens to be minus 1 unit, let's say to the left, will come to a point which is going to be equal to tau equal to t minus 1. It's 1 unit to the left. Regardless of what t is, I'm going even further 1 unit to the left. Now, you may think minus infinity is already minus infinity. If you subtract 1, you get minus infinity. Yes. Imagine that minus infinity is not minus infinity. It's just a large value, a large negative value. Okay? So clearly, this is going to be 1 unit to the left of that large negative value. If this point, for example, was equal to minus 5, I'll take it all the way to tau equal to t minus 5. Okay? So basically, the figure that I'm going to have now, let me just sketch it, and I think this is the last thing that I'm going to mention. This is how the figure will look like. Tau. So I'll come to that. This is tau equal to t. Tau equal to t minus 1. Tau equal to t minus 5, for example. Okay? And there was nothing in here at 0, but my function looks like this. Okay? Now, I will stop at this point, okay, which is basically the end of point 4. Until now, by the way, we haven't computed okay. Until now, I haven't computed the convolution. All I did is the different steps that will allow me now, in the next step, to find the product of 2 things, which are basically the product of this with this, and then I'll find what is the integration, and this becomes equal to the convolution. And not only that, I'll just find the convolution, believe it or not, at 1 point of t, or for 1 value of t. I will have to do something that will allow me to find now the convolution for different values of t. So until now, we haven't found any part of the convolution. Inshallah, next class, we'll start from this point. And inshallah, once we solve 1 or maybe 2 examples, hopefully you'll understand the concept and you'll be able to find the convolution of any 2 functions that I may give you. Okay? But I'll stop at this point. If you have any questions, please be my guest. I think 1 or 2 of you wanted to review with me your quizzes. And my apologies yesterday, Wallah. I had a meeting that started at 2 p.m. and it finished at about 4:30 or 5 something. But by the time I reached home, I was so exhausted. I was not able to. I think one of you called me. I'm not sure whether it was from your class or the other class. But I remember that someone called me on Teams, and I was not able to respond. But if you have the time today between 1 and 2, you can just give me a call on Teams if you want to review your quiz. I'll be happy to review it. or even if you call me probably in the evening or so, I'll be happy to answer you. Okay, Juan? Okay. اتفضل يا جهاد.
دكتور لا انت ممكن تحط السولوشن حق الكويز الاول او الثاني؟
ان شاء الله. Okay. I'll put the solution for at least quiz 1. I'll put it in the lecture notes instead of just writing it. In fact, I was planning to do this, but I didn't have the time yesterday to do it. I will put the solution of the quiz number 1, probably even quiz number 2. I'll put it as examples, let's say, in the same lecture note. Which I'll upload it probably I'll upload it maybe tomorrow or so. Okay?
يعطيك العافية.
حياك الله. Well, my apologies for the delay. I should have given it to you much earlier. Okay, تفضل أحمد.
Doctor, could you upload the latest version of the lecture notes so we can prepare before tomorrow?
Sure. خلاص. Just okay. What I will do is الآن طبعا خلص the class. Probably I will have I have a meeting I think at about I have a meeting sometime later. Okay. Until that meeting, I will maybe do a little bit of updates, and maybe after the meeting by half an hour or so, I promise you that I'll upload at least an updated version. One of the reasons, by the way, I certainly can upload an update after even adding half a page. It's just that I like as much as possible whenever I do an update, I make sure, for example, that the update is valid or is correct from page 1 to page 20. So that when I do an update, I only update, for example, page 20 to 25 or so. So that if you have printed the first 20 pages, you do not need to go and print the first 20 pages again. لهذا السبب when I don't do the update, you see, I have the update and you're seeing it in front of you. But I do not upload it because I do not want to confuse you. لهذا السبب. But خلاص إن شاء الله. Just give me probably a couple of hours. Let me just add a little bit more stuff. Inshallah, I'll upload an updated version for the lecture. Okay?
Okay, take your time, Victor. And I have also another question.
Let me see what Hussein wants, and then I'll attempt your question. Okay? Hussein, you have a quick question?
عندي سؤال بس عن ال HFT. عن الانبوت. إنه ليش
About what we just mentioned?
لا أنا مستغرب ليش شكلها طالع. ولا ممكن يطلع أي شكل مع إنه الانبوت حقها دلتا المفروض.
Okay. Thank you for pointing this out. Okay. HFT, even if you feed an input, which is an impulse, it depends on the system. Some systems, if you feed them with an impulse, they will provide you with an impulse. Some systems, you feed them with an impulse, they provide you with 3 impulses. Some systems, you feed them with an impulse, they provide you with a function that is completely different. It doesn't even look like an impulse. It may look like a step, for example. Okay? So the shape of H has to do with what is the behavior of the system. I'll give you an example. Maybe a practical example. I was even thinking of doing it and putting a picture of it in the lecture notes. And probably I'll do it. We said that if you have a sound system, if you're standing between 2 mountains, let's say, or between buildings or so, you can think of the region around you as a sound system. You're speaking and someone else is listening to you. Right? Think of the path between you and the person who's listening to you as a system. The input goes into that system, it gets messed up, and the other person hears you with a little bit of distortion. If you are standing between buildings, the system that is represented, or let's say the sound system that is represented by the buildings and everything, okay, has an impulse response, which if you put an impulse, which is like a clap, the output will also be claps. Usually this appears if you're in a big room, or let's say between mountains, where if you shout, what do you hear? You hear exactly your voice, okay, but you hear echoes of it, or you hear copies of it, which means that if you put an impulse, you'll hear the same impulses that you have put into the system, but maybe delayed and attenuated. Okay? For such a system, the output, you put an impulse, the output are impulses, 1 or more impulses. If there are no echoes, the output is just a single impulse. If there are echoes, 3 or 4 echoes, you see that the output will be impulses, just like the input. So I want you to take I'll show you what happens here in this building. In this building, I will put an impulse, which is like a clap, and you see that the output is a completely different version. In fact, the output there contains maybe 1 million different echoes. Why? Because my voice, or the clap that I produced, hit one of the walls, it came back to you after maybe a delay of 1 millisecond. Not only that, the same sound that hit the wall and came back to you also hit the wall and reflected back on another wall and came to you a little bit more delayed. So you get another impulse. And this process keeps repeating again and again and again. And the sound basically hits different places and come to you one after the other. So you still see my my screen, right?
Yes.
Okay. So you put into the system an impulse like that, but what you receive at the output of the system is maybe 1,000 or 1 million different impulses. One impulse here, another one there, third one there, fourth. And they are coming almost after each other. And you cannot distinguish between them. They appear to be maybe something like this. But practically, you can think of them as 1 million echoes. For example, okay? If you get echoes that are very close to each other, very often they'll approximate the system as having an impulse response. You put a single sound. The impulse response looks like this. And clearly, as the time progresses, what happens to the amount of voice that is coming to you? It attenuates. That's why you put an impulse at t equal to 0, you get sounds that extend until, for example, 3 seconds, or 4 seconds, or 5 seconds. And as the time progresses, as I mentioned, the amplitudes of the different echoes that come to you get attenuated until eventually they die after maybe 5 seconds or so. Okay? So putting an impulse into a system does not necessarily mean that you'll get an impulse at the output. It depends on how complicated the system is.
Okay, clear. Thank you.
Okay? Okay. Sure. تفضل أحمد. Ahmed, I cannot hear you. I see your microphone is on, but I cannot hear you. Ahmed, can you hear me? I cannot hear you. Maybe you need to turn it on.
Hello.
Oh, تفضل. Yes, I can hear you.
Doctor, in the example you just gave us, h of tau, shouldn't we shift to the right instead of to the left?
Okay. First of all, I said, good point. H of, the way I wrote it is h of t minus tau. Right? Okay?
Yes.
The minus there flips around the y-axis. Right?
Right.
And think of this, okay, and think of this as h of minus tau minus t. Okay?
Okay.
Right? And I'm setting t to be equal to minus infinity.
Okay.
So practically, what I'm sketching is h of minus and then tau plus infinity. When you set t to be equal to minus infinity, effectively what I have is h of minus. The minus just flips around the y-axis.
Okay, so
When
you
I'm
assume
removing-
it is minus infinity.
Yes, I set, at the beginning, I'm setting t to be equal to minus infinity, yes. Sorry, if I said t equal to infinity, my apologies. What I meant is set t to be equal to minus infinity at the beginning. And
Okay,
then we will
thank you.
increase t. Okay, did I answer your question?
Okay. Yes, thank you.
Sure. Any other questions, gentlemen?